I will continue our lecture today for reaction engineering. Let me share the screen first. Okay, so before I start, let me recap first what we have learned last week on chapter 3, so that then we can continue with the lesson after this. Right. So we already actually entered chapter 3 last week, where we started a little bit on the rate law. Okay, so I already taught you a little bit on determining minus RA, the rate of reaction. Okay, so you have to remember, before this, in chapter 2, you have seen the minus RA, okay, in the form of a table or in the form of a Lorentz-Beer plot, where using the information of X conversion versus the minus RA, you will use it to determine the volume of PFR, the volume of CSTR. Okay, so in chapter 3 now, we will learn how to actually calculate the value of minus RA. So chapter 2, nilai tu terus diberi. Dalam chapter 3, we learn actually macam mana kita nak determine the value of minus RA. Okay, so the minus RA is determined using the power law model. So power law model says minus RA equals to first K. So K is the reaction rate constant. Ca, Cb is the concentration of your reactant. So let's say we have reactant A, reactant B. So we have concentration A, concentration B. Then we have alpha and beta. So alpha and beta is the reaction order. Okay, so that was what we learned last week. Okay, then after that, we also determine how do we know the reaction order. Okay, macam mana kita nak tahu reaction order with respect to the reactant in the rate law. Okay, so to determine the reaction order, it depends whether the reaction follows elementary rate law or the reaction is non-elementary rate law. Means dia tak follow rate law. Dia tak follow elementary rate law. So what does this mean? Okay, if the reaction follows elementary rate law, only and only if the reaction follows elementary rate law, means kalau dalam test dan exam is stated clearly, the reaction follows elementary rate law or the elementary reaction, something like that. The word elementary is there, then you may assume it's elementary rate law. Okay, if it's not stated, then you may not assume that. Okay, so what happens if it's elementary rate law? If the reaction follows elementary rate law, reaction order for the reactant, for the concentration, follows the stoichiometric coefficient. Okay, what is a stoichiometric coefficient? That's the number in front of the species in the chemical equation. Maksudnya, for example, if you see on the left-hand side, we have the reaction is 1A reacting with 2B to produce 2C. Means you have 1A reacting with 2B, produce 2C. Hence, in the rate law, the reaction order for A will be 1, first order. The reaction order for B will be second order, 2. That's why you see the rate law become minus RA equals to K is always there, regardless elementary rate law ke non-elementary rate law, the K is there. The K is reaction rate constant. Beza, minus RA is reaction rate. K is reaction rate constant. So you have Ca, concentration of A, power of 1 sebab in front of species A in the chemical equation is 1. Walaupun dia tak tulis 1, you know, right? If it's not even written in the chemical equation, it means it is 1. So first order with respect to A, so Ca power of 1. So when something power of 1 is actually still the number. Meaning katakan 4 kuasa 1 masih 4. That's why Ca kuasa 1 masih Ca. So you just put it as Ca. Then Cb power of 2. So why power of 2? Because the stoichiometric coefficient in front of the species B is 2. So you get the rate law minus RA equals to K Ca Cb power of 2. Okay, so that's how we elucidate or we deduce the rate law based on the assumption this follows elementary rate law. Okay, however, for the cases where the reaction is non-elementary rate law, katakan untuk tindak balas tu stated it does not follow elementary rate law. Means dia adalah non-elementary rate law. You can no longer deduce the order by looking at the chemical equation. Maksudnya tertib tindak balas tu, reaction order tu kamu dah tak boleh tengok persamaan kimia dia. So how do we get it? Okay, for this kind of cases, the information has to be given to you. Okay, information tu either kalau macam dalam test dan dalam exam, I will clearly state what's the reaction order. Tapi kalau katakan in the normal application, then you have to check from literature, you have to check from other resources. Means dia punya tertib tindak balas tu dah tak mengikut the stoichiometry coefficient. So for example, in this case, you have a similar reaction. Katakan 1A reactive with 2B produce 2C. Okay, so dia kata this is non-elementary rate law and stated the reaction is second order with respect to A and zero order with respect to B. Okay, so stated reaction second order with respect to A and zero order with respect to B. So what is the rate law? So rate law dia akan menjadi minus RA equals to K. K is still there, don't forget. Now becomes CA power of 2. Why power of 2? Because this says reaction dia second order with respect to A. Then what about B? Okay, so dia kata for B, zero order. So CB power 0 is actually 1. That's why you see there's no more CB there because CB power 0 is 1. So the rate law become minus RA equals to KCA square. So you must understand, ini beza dia, elementary rate law dan elementary rate law. Kalau elementary, you look at the chemical equation. Non-elementary rate law, it does not follow the stoichiometry coefficient anymore. So I did explain last week kenapa. Kamu kena faham, reaction does not means not necessarily only one kind of mechanism taking place at one time. Although in one reaction you have several mechanism. Contohnya mungkin dalam case ini, okay, let us deduce, okay, walaupun tindak balas dia di antara A dengan 2B untuk menghasilkan 2C, but perhaps in the mechanism, what happen is the A kena bergabung dulu. The A has to combine first, then only can react with the B, something like that. So the mechanism can be different mechanism, but the rate law must be based on one mechanism, or I would say the most significant rate determining step. So rate determining step itulah yang kita akan dapatkan rate law dia. So don't be surprised kalau rate law dia tak mengikut persamaan kimia. That's very common if you have reaction with different mechanism. Okay, yang penting kamu kena faham beza elementary rate law dan elementary rate law. Okay, next. Now, let's talk about K. Okay, we already talk about minus. We already talk about reaction order. Now we understand K. Okay, so what's K? So as I told you, K is a reaction rate constant, and actually you have to understand the unit of K will change according to the rate law. Okay, so kenapa dia boleh berubah is because, okay, we know rate law mesti minus RA equals to K, katakan CA alpha, CB beta. Okay, the unit for your minus RA is always the same, not unit. The dimension of the minus RA will always be the same. Maksudnya minus RA dimension dia adalah concentration per time. So if you forget, minus RA is the rate of reaction, kadar tindak balas. So, how we measure the rate of reaction? We measure the concentration of A with time. Sebab tu kadar tindak balas adalah sama dengan perubahan kepekatan A terhadap masa. So, minus RA dimension dia sentiasa concentration per time, concentration per time. Tetapi kalau kamu perasan, kalau di kiri, on my left hand side, the dimensions are constant. Therefore, on the right hand side, unit K ni akan berubah. Sebab dia bergantung kepada reaction order kan. Okay, apa maksud dia? Okay, first of all, let us try. Katakan sekarang kita ada zero order reaction. Okay, so zero order reaction, maka minus RA sama dengan K. Maksudnya, kedua-dua kepekatan A dan B, katakan CA is power 0, CB pun katakan power 0. So both power 0, 1, 1. So you are left with minus RA equals to K. So dalam senario ni kamu akan tengok, you learn this before in CPP, maknanya dimension ataupun unit di belah kiri akan sama dengan unit dan dimension di belah kanan. Means kalau belah kiri dimension saya concentration per time, So concentration contohnya unit dia katakan mole per dm cube second, let's say. So concentration per time, unit dia katakan mole per dm cube second. So on your right hand side pun, automatically unit K, dimension K pun akan ikut dimension minus RA. Means K punya dimension pun concentration per time. So it can be mole per dm cube second, mole per liter hour, so on and so forth. So kalau zero order, dimension K, concentration per time. So kalau kamu tengok unit dia, dia akan jadi mole per liter saat. Ataupun like I told you, kalau American Engineering Unit, pound mole per feet cube second. Okay, so that's it for zero order. Okay, I said it's going to be different for reaction order kan. So let us go to first order pula. Okay, so kalau first order, minus RA sekarang akan sama dengan either KCA or KCB. Okay, kita katakan kita tak sure. We don't know whether it's KCA or KCB, tapi kita tahu dia adalah first order. Regardless whether CA ke CB ke, let us check the dimension. Okay, so kalau belah kiri, dimension dia masih concentration per time. Okay, minus RA punya dimension takkan berubah. Kamu just ingat, kadar tindak balas ni kita kira sebenarnya mengikut perubahan kepekatan A dengan masa. So kamu just imagine minit kosong, saya kira kepekatan A. Minit pertama, saya kira kepekatan A lagi. So on and so forth. So the dimension is always concentration per time. Okay, what about belah right? So on the right hand side, katakan dimension K kita tak tahu. Okay, kita nak cari dimension K. And kita tahu kalau CA tu concentration kan. So dimension dia concentration lah. CA tu concentration. CB pun concentration. Either way pun dimension dia masih concentration. So when you put it as equal, you can already get the dimension of K as 1 per time. Maksud dia kalau reaction tu first order, unit K akan menjadi per second, per minute, per hour, per day. So kamu tengok dah berbeza kan, kalau zero order dia punya dimension concentration per time, mole per liter second, mole per dm cube hour, so on and so forth. Tapi kalau first order dia punya dimension is per time. So jadi per hour, per minute, so on and so forth. Okay. What about second order? So second order pula, dia ada banyak senario kan, sebab second order can be minus RA equals to KCA power of 2. Second order. Dia boleh juga menjadi KCB power of 2. Second order juga. It can also be KCA CB. Kenapa dia second order? Sebab CA power 1, CB also power 1, 1 plus 1 is 2. So total order dia pun masih 2. So what happens to the dimension of K? So left hand side, concentration per time. Right hand side, dimension K we want to find. It become multiply concentration power of 2. Kenapa power of 2? Sebab CA kuasa 2 atau CB kuasa 2. CA, CB pun masih concentration kuasa 2. Okay, so in that case, you will get the dimension of K sekarang dah menjadi 1 per concentration time. Ataupun contoh unit dia akan menjadi liter per mole second. Concentration tu unit dia terbalik. So jadi liter per mole second, feet cube per pound mole hour, can be dm cube per dm cube per kilomole second, so on and so forth. So you can see here, the units and dimension of K change with the reaction order. Okay, so perhaps you might wonder, why do we need to know this? There's always a reason why. Kan kenapa kita nak tahu unit K tu berubah, apa kepentingan dia? Okay, the significance of knowing the dimension or the unit and dimension of K is because, let's say you can actually deduce reaction order dia dengan melihat unit dan dimension dia. Contohnya katakan, let's say you're looking for literature, you have a reaction, you're looking at the literature, okay? You know, katakan dalam literature tu reaction dia adalah satu reaktan saja. Katakan reaktan A, okay, kamu tak sure dia punya rate law, okay? Kamu tak dapat information pasal rate law dia, ataupun dia tak cakap reaction tu elementary rate law ke non-elementary rate law. The only information dia bagi adalah unit K. So katakan unit K tu adalah per second. Okay, so dia kata dia bagi, let's say the value of K is 10 per second. So from the unit of the K, you know that per second dimension dia adalah per time. So per time kamu tahu daripada kita yang baru belajar, meaning most likely reaction tu rate law dia adalah first order. And since kita ada satu reactant saja, definitely dia adalah first order with respect to A. So same case, katakan you have only reactant A dalam reaction tu, kamu tengok unit K dia adalah liter per mole hour. So liter per mole hour, you know dimension dia 1 per concentration time. So kamu tahu 1 per concentration time, most likely daripada yang kita belajar sini, reaction dia, rate law dia adalah second order. And sebab dia hanya ada satu reactant, definitely dia adalah second order with respect to A. So kamu dah boleh write down the rate law. So minus RA equals to KCA square. Previous one, minus RA equals to KCA. Okay. However, okay, although this is good to use the dimension to deduce the rate law, tapi dia ada limitation juga. Okay, maksudnya kalau kita ada satu reactor, then okay. Sebab kalau first order, mestilah first order terhadap A. Kalau second order, mestilah second order terhadap A. So you definitely can straight away write down the rate law. However, kalau kamu ada dua reactant, so let's say your reaction got two reactant, it's a bit hard for you to deduce exactly. Sebab katakan kamu dapat unit K tu, kamu deduce dia adalah first order. So kalau kamu ada dua reactant and kamu tahu dia adalah first order, dia ada dua kemungkinan. It's either first order with respect to A, minus RA equals to KCA, or it can also be minus RA equals to KCB, first order with respect to B. So in that case, although you know it's first order, okay, from the unit of K, but you cannot pinpoint exactly rate law dia sebab dia boleh jadi first order terhadap A atau first order terhadap B. Similarly, kalau second order, so let's say you find from literature, you see the K unit, the dimension, you know it is second order. Okay, tetapi although you know it's second order, kamu tak boleh juga pinpoint exactly the rate law because dia ada three possibility. It can be second order with respect to A minus RA KCA square. It can be second order with respect to B minus RA KCB power of 2. Or it can also be minus RA equals to KCA CB. Also second order because 1 plus 1 or the first order tambah first order is still second order. Unit K dia masih sama unit untuk second order. Okay, so in that case, bila ada dua reactant, you can somewhat deduce dia first order ke, zero order ke, second order. Tapi exact rate law kita takkan tahu. Tapi kalau satu reactant, you can definitely pinpoint terus dia adalah first order ke, second order terhadap A. Okay, so that's why sometimes knowing the unit and dimension of K plays a part in elucidating the rate law. Okay. So we are done on K, knowing the unit K in relation to the reaction rate constant. Okay. Next is we're going to learn about elementary rate law and molecularity. Okay, so this is just a basic knowledge. Molecularity is the number of atom, ions or molecule involved colliding in a reaction step. So I told you before kan, kalau macam contohnya, okay, contohnya katakan I told you just now, kalau reaction tu second order, most likely it's actually involving two molecules, right? So it not necessarily only molecules, it can be atom, it can be ions. Okay, so maksudnya if you have unimolecular, bimolecular, thermolecular reaction involve 1, 2. Okay, kalau 1 unimolecular, bimolecular 2, 3 molecular, thermolecular, atoms or molecules interacting or colliding in any one reaction step. So we name it as, kalau ada dua molecule reacting, we call it as bimolecular reaction. 1 is unimolecular, thermolecular means 3 atoms or molecules reacting together. Okay, so that's just the term that we use, right? Okay, done on that part. Okay, this is just, that one was just theory. Now we go to another important thing. K. Tadi kita tahu sikit pasal unit dimension K. Now we want to know how to calculate K. So throughout the whole chapter of reaction engineering, you will keep looking, you will keep doing calculation in relation to K, reaction rate constant. Okay, so selain daripada is called as reaction rate constant, it's also called as specific reaction rate. Okay, so again I repeat, selain daripada kita panggil K itu sebagai reaction rate constant, kita juga panggil dia sebagai specific reaction rate. Okay, so 1, 2, okay, reaction rate constant K is very sensitive towards temperature. Maksudnya, katakan kamu ada satu tindak balas, kalau kamu ubah nilai suhu of the reaction, either you increase or you decrease the temperature of the reaction, the value of K will and must change. Sebab tu kamu tengok signifikan kenapa. Cara senang untuk kamu faham kenapa kadang-kadang certain tindak balas kita naikkan suhu. Kenapa? Sebenarnya sebab kalau kamu perasan mathematically kan, bila kita naik suhu, nanti kamu akan tengok dalam equation. I will introduce you an equation yang will relate K with temperature. Okay. So for the equation nanti kamu akan tengok temperature akan menyebabkan nilai K naik. Means I increase temperature, K increases. Okay, so kalau kamu tengok daripada persamaan dalam kotak kuning ni, if my K increase, naturally my minus RA pun akan increase. Means kalau reaction rate constant, temperature naik, K naik, reaction rate pun naik, kadar tindak balas pun naik. Okay, kalau kamu ingat kamu pernah belajar kan, reaction rate ni kan berkaitan dengan volume reactor. So sebab tu design reactor tu, volume reactor tu akan terganggu ataupun the design will be affected by the change of temperature. Okay, so that's one important thing. So kamu tengok kenapa pengiraan dia akan berubah sebab minus RA akan dikacau. Kenapa minus RA dikacau? Sebab K dikacau. Kenapa K dikacau? Sebab suhu telah dikacau juga. So that's the correlation. Okay, next. K is also affected by the presence of catalyst. So salah satu cara sebab kita sentiasa nak nilai minus RA yang tinggi. Kenapa kita nak nilai minus RA yang tinggi? Kalau kami ingat balik, minus RA kan kepekatan A terhadap massa. So kalau nilai minus RA tinggi means more A is consumed during the reaction. Means more A will disappear. So kita sentiasa cuba nak naikkan minus RE. So salah satu cara naikkan suhu. Naik suhu, K naik, minus RE naik. Sebab tu certain reaction kamu tengok we will use heat. So why do we use heat? Is essentially to increase minus RE and to increase the reaction. Okay, another way kalau kamu tak nak kacau suhu is to use catalyst. The same. Bila kamu guna catalyst, we actually increase the K, which I will explain later how the K will be increased because of the use of catalyst. So salah satu cara dia daripada suhu is guna mangkin, K naik, minus RA naik, kadar tindak balas pun akan naik. Okay, then also depends. Kalau you are using gas phase reaction, katakan your reactor in gas phase, you may also increase the K by increasing the pressure. Dia also boleh membantu. Or in liquid system, it can be it can be dependent on the ionic strength and the choice of solvent. Cara lain kalau ada liquid, okay, for you to manipulate the value of K. Tapi the concept is kita nak K as high as possible. K tinggi minus RA tinggi means more A is consumed in the reaction. Okay, now we go to the equation that relate K to temperature. So I think you have probably seen this equation before, but if you don't, let me introduce again. This is what we call as Arrhenius equation. Okay, so Arrhenius equation ni konsep dia adalah dia mengaitkan if it founds a correlation. So this Arrhenius actually is a person. Okay, actually I think he won the Nobel Prize for this for coming up and proving the theory of this equation. I think it was in 1980. Oh, it's almost 100 years, more than 100 years equation. So you're actually learning an equation which is more than 100 years. So this Arrhenius, okay, he found by theoretical and by experimentally that the value of K is correlated to the temperature by this equation. So this says K, the reaction rate constant, equals to A. So A is your pre-exponential factor or frequency factor. Okay, so hari ni kamu belajar satu lagi extra equation, tambahlah lagi alphabet yang kamu kena belajar. So macam reaction, I admit there's a lot of alphabet that you kena familiar. Tapi the good thing is nanti dalam chapter, now is chapter 3, right? Chapter 4, chapter 5, chapter 6 kamu jumpa je balik K ni, kamu jumpa balik saja almost the same alphabet. Okay, so K equals to A. A is the frequency factor or we call it pre-exponential factor, either one pun sama maksud dia. Dan exponent, okay, exponent sedang calculator, make sure you know how to press exponent. Power, exponential power in bracket negative. So negative is there, don't forget, is negative EA per RT. Okay, so again, K is correlated with equals to A exponential power minus negative EA per RT. Okay, so what does it mean? Okay, first of all, as I told you, A kamu dah tahu, EA. EA is activation energy, which I will teach you a little bit later. What's the concept of activation energy? Per R gas constant, T is temperature. Okay. Before this, you have learned gas constant kan? Masa kita belajar pasal ideal gas law, nak cari the concentration of A, Ca0, you have seen the gas constant. Okay, that gas constant, the R value, that one is for the ideal gas law. Okay, kamu tahu kan R ada banyak value kan? R got different value depending on the unit. Okay, the one that you learn are 8.3144, apa lagi kamu belajar? One something, the numbers, that one is for the ideal gas law. They are also gas constant in this equation, and for these two equations, the R is for the energy calculation. So the R for the energy calculation in this equation is only either one. Either you use 8.314 joule per mole Kelvin or 1.987 calorie per mole Kelvin. So kenapa dia special? Sebab inilah R value ni ada unit energy, which is calorie or joule. So kalau kamu ingat, kamu belajar kan energy unit dia calorie or joule, the common one. So oleh itu, that's why these two R value is to be used for the calculation of energy. Okay, so kamu janganlah guna yang 8.3144 kilopascal dm cube per liter. That one is for the ideal gas law. Okay, unit dia dah berlainan. Kenapa saya kena cakap ni? Sebab kadang-kadang I know when you have a lot of R value, you got confused nak satu yang nak guna. Okay, so just remember kalau Arrhenius ni either 8.314 joule per mole Kelvin or 1.987 calorie per mole Kelvin. Okay, so this is the correlation between K and temperature. So if you see here mathematically, you should be able to see that K and temperature is directly proportionate. Means if T increase, K will increase. Okay, again I repeat, if temperature increases, the value of K increases. So kalau K meningkat, minus RA pun meningkat, means kadar tindak balas akan meningkat. That's why sometimes in reaction, we will actually use higher temperature. That's the reason. Okay. Now, we go towards activation energy. Apakah itu maksud activation energy? So, activation energy kita guna EA, okay? EA. Okay, how do I explain activation energy in a simplest way? Okay, for a reaction to occur ataupun for one reaction to happen, the reactant tu punya molecule must have this minimum energy before the reaction can take place. So this minimum energy is what we call as activation energy. So kenapa molekul ni perlukan tenaga minima ini? Because they require the energy to distort or stretch their bond in order to break and form new bonds. Kamu tahu kan tindak balas berlaku melibatkan the breakage and the formation of bond. So certain bond kena break, certain bond need to be formed. Baru tindak balas tu berlaku untuk menghasilkan produk yang baru. Okay, so in order for that bonds to break and combine and form, the molecules tu kena ada certain amount of energy first, which we call as activation energy. Okay, sebab tu kalau kamu perasan, in certain reaction, kenapa mula-mula kita panaskan? Okay, kenapa kita panaskan is actually we are providing energy to the molecule with the hope that the energy that you provide is sufficient for the breakage and the combinations, the breakage and the formation of the new bond. Then only a reaction can take place. So, favorably, kenapa activation energy ni is something good? Okay, you just imagine. Okay, let's say sekarang kamu katakan kamu nak menghasilkan this new chemical. So, let's say the chemical is chemical C. Okay. So, let's say you found from your study, from your literature ke apa, you found ada jenis tindak balas yang berlainan. Katakan ada 2-3 jenis tindak balas yang berlainan yang boleh menghasilkan produk C. Okay. So how do we compare, nak tahu mana satu tindak balas yang baik? Of course, there's a lot of criteria. Tak boleh cakap hanya satu criteria sahaja. Okay, but one of the main criteria that you can use is by looking at the activation energy. Comparing the activation energy. So, katakan nak hasilkan produk C ni, kamu jumpa the teacher ada dua cara yang berlainan. Okay, dua tindak balas yang berlainan. So, let's say dia kata the first tindak balas ni, activation energy dia adalah 10 kilojoule per mole. Tindak balas yang kedua, salah satu bicara, dia punya activation energy katakan adalah 5 kilojoule per mole. So naturally kamu tahu kan, reaction yang memerlukan tenaga yang paling sedikit adalah tindak balas yang lebih baik. Sebab dia hanya perlukan 5 kilojoule per mole, dah berlaku tindak balas tu. In comparison tu, tindak balas yang satu lagi, dia perlukan tenaga sebanyak 10 kilojoule per mole. Baru tindak balas tu boleh berlaku. Ataupun erti kata lain, if I ask you to climb Kinabalu and to climb katakan Bukit Tampin, of course it's easier for you to climb a Bukit Tampin because it's much lower than climbing a Mount Kinabalu because it's a much higher for you to climb. So that's the same concept. We always choose the reaction with lower activation energy. However, that's not the only criteria untuk tindak balas sebab kamu kena consider juga. Okay, mungkin tindak balas tu activation energy dia rendah tetapi mungkin raw material dia adalah mahal. Okay, you have a very good reaction but your raw materials are expensive. So that is also a factor. Okay, so not necessarily only looking at activation energy, but it is one of the criteria that people will look when we want to consider different types of reaction to produce a certain product. Okay, so that's on the understanding of activation energy. Okay, so EA. Right, so next is how do we calculate? Okay, kita dah tahu persamaan Arrhenius tu. Let us try to calculate using the Arrhenius equation untuk tahu nilai K. Okay. So let's say example in this question, A and B react to form C with an activation energy of 3 kilojoule per mole and a pre-exponential factor of 0.5 liter per mole minute. Okay, so I already taught you, right? Bila ada soalan engineering or reaction engineering, understanding the information is very vital before you solve it. Okay, so first benda dia kata activation energy 3 kilojoule per mole. So sebab kita pun baru belajar, kita pun ingatlah kan activation energy itu adalah EA. So EA 3 kilojoule per mole. Okay, next. Pre-exponential factor. So A dalam Arrhenius equation kita ada A. So A tu adalah 0.5 liter per mole minute. Basically kalau kamu nampak dalam soalan ke, dalam literature ke, if you see ada EA, ada A, definitely is to do with Arrhenius equation. Okay, very likely dia akan berkaitan dengan Arrhenius equation. Okay, so dia kata calculate reaction rate constant K at 70 Celsius. So again, okay, kita come back to the Arrhenius equation. So as I always keep telling you, teaching you, satu equation kalau nak solve kena hanya ada satu unknown. Yang lain semua dah kena ada nilai. Kalau kamu ada satu unknown, satu persamaan boleh solve. Kalau satu persamaan, dua unknown memang takkan boleh solve sampai bila-bila. So in this equation meaning I want to find K at 70 Celsius, which is my left hand side. Meaning on my right, segala unknown on my right, I have to substitute with values. So first of all, A. So A is the pre-exponential factor. So it is 0.5 liter per mole minute. So you replace. Exponential, okay, exponential, please learn how to press the calculator. Exponential, that in bracket negative. So negative ni jangan lupa sebab often cases student lupa negative sign. Sebab nanti saya akan tunjuk satu lagi version equation ni. So version kedua tu tak ada negatif. So students sometimes get confused. So yang kamu belajar setakat ni is the original version of the equation. Okay, so ada negatif. Negatif EA. Okay, so EA per RT. Okay, so EA so EA now become ada negatif 3 kilojoule per mole. Okay, so 3 tu kilojoule per mole tu we convert into joule per mole. So kenapa kita convert the 3 kilojoule per mole become 3000 joule per mole. Okay, kamu tahu kan, kilo tukar kepada kilo, joule kepada joule nak tukar darab 1000 je. Sama je macam kilometer tukar kepada meter darab 1000. The same concept. So, multiply with 1000, we get 3000 joule per mole. So, why do I multiply with 1000? Because unit K. So unit K dia kan tadi saya ajak, dia ada dua kan, either 8.314 joule per mole Kelvin or 1.987 calorie per mole Kelvin. So in this case, I'm using joule, my EA is in joule, so that's why I will use my R value 8.314 joule per mole Kelvin. Sebab tu kilojoule, saya tukar kepada joule sebab unit R saya dalam bentuk joule. So don't forget that part. Kadang-kadang student pun macam seniors kamu terlupa part ni sebab nilai R tu dalam bentuk joule. So unit A tu, unit EA you have to change into joule. Okay, so just multiply with 1000. Then bottom, multiply with T, temperature. So again, because the R value unit dia adalah Kelvin, because the temperature unit in the R value, in the R gas constant is Kelvin. So the temperature that I use 70 Celsius, I have to convert into Kelvin. So just plus 273.15, straightforward lah, Celsius to Kelvin. The conversion factor, you just add 273.15. So when you multiply, okay, you will get the K value. So in this case, I did not solve the K value. When you have time later, please solve and to find out yourself so that you practice a little bit of calculation to determine the value of K. So everything dah bagi, just kamu tekan je calculator untuk tahu berapa nilai K dia. Okay, so this one I think is not a big problem, memang definitely can be solved. Okay. Then remember I told you Arrhenius equation ni dia ada version kedua. Okay. Sama je, dia tak adalah beza, just that I would say ni adalah equation terbitan. Okay, maksud what do you mean by in English extension of the equation. So what is the difference? Okay. Now, case yang tadi, equation yang tadi yang kamu guna, maybe I go first to the back one. Okay. Equation tadi yang kamu guna, okay, you want to find K. Okay, if you know A, EA dan temperature, you need to know three things. A, EA, temperature, you can find the K. Okay, now let's say in a situation of which kamu dah tahu K pada suhu 70, katakan, okay, kamu dah tahu K pada suhu 70 Celsius, kamu nak cari K pada suhu yang baru, let's say 100 Celsius. Okay, so you can find the new K, okay, kita katakan kamu dah tahu K1 pada T1, kamu nak cari K2 at new temperature, T2. So saya dah tahu K1, saya tahu T1. Saya nak cari K2 pada T2 yang saya dah tahu. Katakan saya nak tahu K2 pada suhu 100. Okay, you may use the second version of the equation. Sebab second version ni lebih senang sikit, lebih cepat sikit. Sebab dia dah tak perlu tahu A. Kalau setakat dah asalkan tahu K1, T1, T2 dan EA, activation energy, kamu dah boleh cari K pada suhu yang baru. Okay, maksudnya as I told you, you have known K1 at T1, you want to find your new K, K2 at a new temperature, T2, with only knowing the activation energy, kamu dah boleh cari. Dan equationnya diberi sebagai K T2, subscript T2 tu masuk K pada suhu yang baru. Bukan darab dengan T2 tapi menunjukkan K pada suhu baru. Kan saya remind kan, K berubah dengan suhu. You have to always remember this. K changes with temperature. So kalau tu tidak balas kamu berubah, nilai K tu kamu kena kira balik nilai K yang baru. So K at the new temperature equals to K at the old temperature or at the original temperature multiply with exponential again, in bracket dah tak ada sign negatif. So sebab tu yang part student seniors kamu kadang confused sebab yang original equation ada negative sign. Yang terbitan ni equation yang version yang kedua ni tak ada dah negatif. So become EA per R, which you have learned, activation energy over gas constant, dalam bracket jadi 1 per T1 suhu asal tolak 1 per T2 suhu baru. Okay. If you wonder kenapa negative sign tu hilang, sebenarnya sebab dalam kurungan ni patutnya negatif tu ada. Kalau negatif tu jadi negatif EA per R, dalam kurungan tu akan menjadi 1/2 tolak 1/1. So dia nak hilangkan negatif tu, so dia darabkan dia kat dalam kurungan. So dalam kurungan sekarang jadi 1/1 minus 1/2. Okay, so I did not show the way for you to derive this equation, okay. Tetapi sebenarnya itu dah explanation dia. Kenapa negatif tu hilang? Sebab negatif tu darab dalam kurungan. So sekarang dalam kurungan tu jadi 1/1 tolak 1/2. Okay, so that's why. Right, so this is the second version of the equation. Beza dia, equation pertama, kalau kita nak kira K, kita tahu A, EA, temperature. Equation yang version kedua ni, okay, adalah bila you know K1 at T1, you want to find the new K at T2 by knowing the new temperature T2 and just by knowing EA. Dah tahu EA, kamu dah boleh cari. Okay, so itu beza dia. Okay, now sebelum saya lupa juga, okay, kejap, what is this? Okay, so now let's see one example. Dia beri kita sekarang, okay, given reaction rate constant 1.5 liter per mole minute at 80 Celsius. So macam saya ajar kamu kan, kalau kamu tengok K ni, unit dia adalah, reaction rate constant kan, unit dia adalah liter per mole minute. So kalau kamu perasan dalam bentuk dimension is 1 per concentration time. So kalau kamu ingat, kalau dimension K tu 1 per concentration time, most likely dia adalah second order reaction. Tu je. Tapi kita tak tahu lah rate law dia apa, kita tak tahu. Tapi kita tahu dia adalah second order reaction. So this K 1.5 ni adalah pada 80 Celsius. Okay. Dia beri activation energy 5 kilocalorie per mole. So dah berubah tadi joule, kilojoule. Yang ni contoh ni dia beri dalam bentuk kilocalorie. Okay. Calculate reaction rate constant at 120 Celsius. So basically dalam soalan ni diberi kita K80 equals to 1.5. They ask us to find K at 120. Okay, so K1 1.5, T1 80 Celsius, K2 berapa? T2 120 Celsius. So you just replace into the equation. So K120 yang saya nak cari equals to K80 yang saya dah tahu. Exponential EA per R in bracket 1 per T1 minus 1 per T2. So you replace K1 as 1.5. Exponential in bracket, okay, sebab R value dia, now we will use 1.987 calorie per mole Kelvin. Okay, we will use R value sebab saya punya nilai EA saya dalam bentuk calorie. So I use 1.987 calorie per mole Kelvin. So but don't forget, since it's calorie and the value given to us is in kilocalorie, you must again multiply 1000. Sama je. Kilojoule ke joule darab 1000, kilocalorie ke kalori pun darab 1000. So you multiply 1000. So 5 kilocalorie per mole become 5000 calorie per mole. So you divide with your R value in bracket again sebab R value dalam bentuk Kelvin. So the temperature unit in the R value is Kelvin. So the temperature, both temperature kamu kena tukar ke dalam bentuk Kelvin. Don't forget, persamaan dia adalah 1/T1 tolak 1/T2. So kalau kamu terbalik jawapan kamu salah, you multiply, you will get the value of K at 120. Okay, so now what are the ways kamu nak check pengiraan? Okay, so kadang-kadang kamu kira ni, kamu perasan equation dia panjang kan, so the tendency to do mistake is very big. Ataupun kadang-kadang kamu tersilap 1/T1 tolak 1/T2 ke, 1/T2 tolak 1/T1 ke. Okay, konsep dia, kalau nak check equation, senang je. One thing is, kalau kamu perasan daripada Arrhenius equation, saya dah ajar kamu kan. K meningkat, temperature increase, the value of K will increase. So maksudnya, naturally, logically, K at 120 Celsius must be bigger value than K at 80 Celsius. So meaning katakan kalau kamu kira K at 120, kamu dapat lebih kecil daripada 1.5. Katakan kamu dapat 1. So kamu dah tahu mesti jawapan kamu tu salah. Sebab nilai K mesti meningkat dengan suhu. One thing. Second, kadang-kadang dalam pengiraan tak semestinya kamu disuruh cari K. Mungkin kamu dia beri nilai K, kamu kena cari EA. EA also, the value must always be a positive value. So kalau kamu dapat negatif EA, kamu check balik pengiraan, must be mistake somewhere else. Okay, must be something else or something wrong in your calculation. Mungkin kamu tertukar ataupun negative sign kamu tersalah letak. Tetapi EA must always be positive. Okay, first EA mesti positif. Kedua, nilai K mesti meningkat dengan suhu. So that's two way for you to check the calculation. Okay, alright. So next, then one more thing that before I forget, kadang-kadang student akan confuse berkaitan K, EA dan A. Okay. Ni konsep dia adalah, okay, kamu just remember you have one reaction. Okay. So nilai untuk satu tindak balas ni, nilai EA dan nilai A dia adalah sama. Regardless kamu tukar suhu ke, kamu tukar tekanan ke, nilai EA dan A akan sama untuk tindak balas itu. Kalau kamu tukar tindak balas, then yes, nilai EA dan A akan berubah. Tapi kalau tindak balas adalah sama, kamu naikkan suhu, kurangkan suhu, EA and A will never change because it's specific to the reaction. Yang akan berubah hanya nilai K untuk tindak balas itu. Kenapa? Sebab K dipengaruhi oleh suhu. Maksudnya kalau kamu ubah suhu, EA dan A takkan berubah. Yang berubah hanyalah nilai K. Okay, that part you really have to understand. Nilai EA dan A tak berubah untuk when you change temperature, EA dan A tak berubah. Tetapi yang berubah hanyalah nilai K. Okay, so done on that part. Now, how do we determine EA dan A? Tadi saya cakapkan pasal kita cari EA, kita cari A. Tapi sebenarnya macam mana kita nak cari EA dan A? Okay. Nanti dalam kamu punya lab, okay, this Thursday later I will brief you a little bit about the lab. I'm not too sure. The news is at the moment, lab tu masih ada physical face to face. But then I dengar ada rumours kata mungkin kena postpone. But at the moment, the latest news was is still on face to face. So kecuali kalau ada perubahan, I will inform you by Wednesday lah. But at this moment, please assume the lab is still on. It's still as scheduled on this Thursday. Okay, right. So come back to this. Okay, macam mana kita nak cari EA dan A? Right. So nanti kat lab, when you do experiment, you actually do this for the experiment. If you do experiment 2A ataupun eksperimen 3A ataupun eksperimen 1B pun, kamu sebenarnya akan kaji perubahan suhu. So when you change the temperature, you will actually get different value of K. Kan ingat saya kata K berubah dengan suhu kan? Okay. So nanti dalam lab, kamu akan ubah suhu tindak balas. So you will run, let's say first reaction at 80 Celsius. Okay. So sebelum ni, setiap group kena buat sampai 2 atau 3 suhu. Tapi I want to save your time and because I want to run more experiment, setiap group buat satu je parameter tapi nanti kamu akan share result dia. Means kamu still akan dapat, kamu memerlukan data untuk lebih daripada 2 suhu. Kalau tak, kamu tak boleh buat dia punya, kamu tak boleh cari EA dan A dia sebenarnya. Okay. So now you imagine, for each temperature tu, you will get your value K. So, kamu buat eksperimen, kamu calculate K. So, katakan grup pertama, kamu buat pada suhu 40 Celsius. Katakan T1. So, grup pertama akan kira K1 dia. So, grup pertama akan tahu K1 at T1. Okay, let's say grup kedua, saya ubah suhu. Katakan saya suruh buat suhu yang lebih tinggi. So, grup tu akan buat eksperimen pada suhu berlainan. Dia pun akan dapat K dia. Of course, K dia berlainan. So, dia akan dapat K2, T2. Let's say group 3, group 4 pun sama. Kita akan dapat sekarang 4 combination of K dan T yang berlainan kan. So, katakan kita plot graph. So, kita plot graph dalam belah kiri. Kamu nampak kita plot graph. Kita dah tahu K1, T1, K2, T2, K3, T3, K4, T4. Okay. Daripada 4 data ini, of course kalau lebih suhu kamu buat lebih banyak data lah. Okay. Daripada 4 data ni sebenarnya kita boleh guna untuk cari EA dan A. In fact, 2 pun dah cukup tapi lebih banyak suhu lebih tepat. So how do we determine EA dan A adalah dengan kita at first we have to linearize the Arrhenius equation. So kalau kamu ingat, kalau kita nak plot graph linear, kan kita kena ada persamaan dalam bentuk y equals to mx plus c. So I hope you still remember kalau kita nak plot graph, persamaan kita kena dalam bentuk y equals to mx plus c. Y is for the y axis, x is for the x axis. So M is your slope or your gradient, and your C is your pintasan Y lah, your y-intercept. Okay. So kalau kamu tengok equation Arrhenius yang original ni bukan dalam bentuk Y equals to mx plus C. So kita tak boleh, kalau kita plot graph guna equation ni, kita takkan dapat graph yang linear. Okay, so how do we linearize the equation? It's basically taking natural logarithm, natural ln. Kita lonkan di belah kiri dan kita lonkan di belah kanan. So we ln on the left hand side, we ln on the right hand side. So if you ln on the left hand side, you get ln k. If you ln on the right hand side, you will get first of all ln A. Okay, so ni matematik sikit lah. Kamu lonkan bahagian A tu kamu dapat ln A. Okay. Eksponen ni, bahagian eksponen tu kan eksponen kuasa minus EA per RT. Kalau kamu lonkan, basically apa berlaku? Exponential tu dah hilang. Okay, this is mathematics. I explain in a very simple way. Exponential kuasa minus EA per RT. Kalau kamu lonkan, exponential tu dah hilang. So dia terus jadi minus EA per RT. So kamu nampak ln K sekarang dah menjadi ln A equals to ln A minus EA per RT. Okay, then I rearrange it. I will explain later kenapa kita rearrange. Tapi kita akan rearrange, kita akan dapat ln K equals to minus EA per RT plus ln A. Saya rearrange je. Saya bawa je yang minus EA per RT ke depan, ln A tu ke belakang. Okay. Kenapa saya buat ni? Okay. Kamu kena ingat balik pula. Kita kan nak plot graph kan? Kalau kita nak plot graph, dia mesti berdasarkan data yang kita ada. Kan kami ingat kita nak plot graph, kita kena titik kan? Kita kena point kan? Setiap point tu kan mesti berdasarkan data yang kita ada. Okay. So kalau kamu ingat, asal yang eksperimen yang kita buat, data yang kita ada adalah apa? K dan T. Kita ada K1, T1, K2, T2, K3, T3, K4, T4. That's the data that I have. So, if I lonkan the value, means katakan saya lonkan ln K. Kalau kamu perasan, ln K akan menjadi titik untuk paksi Y saya. Ln K will be my Y axis. So means kalau saya lonkan K1, ln K2, ln K3, ln K4, that will be the data for my for my Y axis, paksi Y. Tapi kamu ingat kalau kita nak plot graph mesti ada data paksi Y, paksi X. So ingat balik, data yang kita ada sebelum ni adalah data temperature. So kalau temperature tu saya reciprocalkan 1 per T, I get the data for my X axis. Maksudnya data X axis saya adalah 1 per T1, 1 per T2, 1 per T3, 1 per T4. So maknanya kalau saya data original saya K1 T1, saya jadikan ln K1 1 per T1, saya dapat titik yang pertama. Data yang kedua, saya ln K2 1 per T2, titik kedua, ln K3 1 per T3, my third point, ln K4 1 per T4, my fourth point. So this 4 point, I can plot a graph. Kalau kamu perasan, dia dah menjadi a linear equation sebab ln K is my y-axis, 1 per T is my x-axis. So naturally, minus EA per R will be my gradient and my y-intercept is ln A. So kalau bayangkan saya plot graph, saya akan dapat straight line sebab it is it's a linear equation. Y equals to mx plus C is a linear equation. Kalau kamu plot 4 point tu, kamu akan dapat dan kamu lukis a straight line, you will get a straight line with a negative slope ataupun negative gradient. Kenapa negative gradient? Sebab kamu tengok equation ni kan negative EA per R. Lepas kita dah ln kan, kita rearrange balik, dia menjadi negative EA per R. Sebab tu gradient saya mesti gradient yang negatif. Okay, so can you imagine? Kamu dah plot graph, kamu dah dapat gradient dia. Katakan kamu kira kecurunan dia. That gradient is equal to your minus EA per R. So, R gas constant kita dah tahu. Kita dah tahu gradient. So, kalau kamu darab, you can get your activation energy. So, that's how you get your activation energy by plotting the graph. Tapi graph dia kena betul ln K versus 1 per temperature. So, gradient equals to minus EA per R. So when you multiply gradient dengan gas constant, you get your EA. So what about A? Okay, dapat equation ln A is your y-intercept. So you plot your graph, you look at the y-intercept. That y-intercept is equal to ln A. Bukan A, dia ln A. Ln A sama dengan pintasan y. So you want to get A, exponential pintasan y. Okay, so you want to get ln A equals to y-intercept. Hence, my A equals to exponential y-intercept. So, that's what you're going to do in our lab. Setiap group run satu eksperimen, betul kita kongsi data, kita plot graph, kita cari EA, kita cari A. Tapi, as I told you, for my case, you don't have to plot manually. Kamu gunalah Excel plot, dapatkan gradient, dapatkan y-intercept, then you calculate your EA dan A. Okay, so that's why we learn how to actually determine EA and A. So, kamu imagine kalau dalam real practical world means kamu run eksperimen, okay, suhu 70, kamu ambil data, kamu kira K. Kamu tukar 80, kamu kira nilai K. Kamu tukar 90, kira nilai K. Then kamu plot graph, kamu dapatlah EA, kamu dapatlah E. Okay, right. So, I have one example here, but this example is an extra homework for you. Sebenarnya tak homework pun, jawapan semua dah diberi. But I would like you to try by yourself to calculate this. So I will not discuss, jalan kerja semua dah ada, jawapan akhir semua dah ada. So I would like you to try this on your own, attempt this on your own later, just to see whether you understand the question or not and whether you understand the solution. Okay, so I will skip this question as a homework for you to do on your extra time. Okay, now I will go to the main part of the chapter 3. So tadi yang kita belajar selama ni, rate law, nilai K, is not yet the main part, tetapi main part ialah apa yang kita akan belajar sekarang, which is actually the most important one. Okay, so this one is what we call as stoichiometric table. Okay. Sebelum kita belajar, kamu tahulah masuk table, means kita akan buat table sekarang. Okay, so sebelum saya start, kamu kena faham, when I explain, it sounds very difficult, which is true. Sebab bila saya explain, dia dalam bentuk simbol. So bentuk simbol ni memang banyak simbol. So always bila mula-mula belajar, memang student akan find it very difficult. However, nanti simbol ni akan digantikan dengan nombor. So when you replace with number, actually the thing is very easy. Just that sebelum kita nak pergi ke nombor tu, kita kena belajar dulu simbol dia. So when you see the symbol, you find it very headache. But later when I explain example, you see the number. Actually, stoichiometric table is not difficult. Okay, but before I go there, you must first understand kenapa kena belajar stoichiometric table. Okay, so I would like always to explain to my student kenapa dia belajar benda tu. So at least dia tahu apa salah I have to go through all this table. Okay. Now, kalau kamu ingat saya ghostan balik, saya pergi kepada rate law. Okay, kita pergi balik rate law jap. Mana rate law dia? Okay, so kita pergi balik kepada rate law ni kan? Okay, so tadi kita dah belajar, kalau kamu perasan, beginning I teach you about alpha dan beta. So kamu dah tahu je nak cari apa tu alpha, apa tu beta, reaction order. So reaction order ada dua kan, elementary, non-elementary. Okay, kamu dah belajar. K, kamu dah belajar pula dengan K. K pun kamu dah tahu cara nak kira K. Means kalau K tu tak diberi, tapi kamu tahu suhu, kamu tahu A, you know EA, you can calculate K. Or let's say you got change of temperature, you can calculate the new K. So you know that. So what's S? What else is left? CA dan CB. Do you realize now? Stoichiometric table ni sebenarnya adalah digunakan to find CA and CB. Itu yang menjadi kompleks dia, nak cari CACB je sebenarnya. Dan juga you can also find the concentration of other compound in your reactor. However, in order to reach that, you have to first learn how to do stoichiometric table. Itu dia punya perjalanan dia. Nak tahu kenapa kita belajar table ni, sebab sebenarnya kamu nak tahu macam mana nak cari CA dengan CB dalam rate law. That's one. Second, kenapa kena baca pasal stoichiometric table? Okay, kalau kamu perasan in CPP, you have learned a mass balance. You already learn mass balance in CPP. Kalau kamu perasan, probably you find mass balance CPP tu very difficult, which I also admit is very hard. And for those student yang under I think all courses also later kamu akan buat design project. Kamu akan jumpa balik juga mass balance ni. Okay. So what is good thing about, kalau kamu perasan, kamu belajar CPP, you have learned mass balance for reactive process. Maksudnya mass balance untuk tindak balas kan. Okay, kalau kamu perasan yang masa kamu belajar tu macam susah sebab kamu belajar method, extent of reaction, kamu belajar atomic balance kalau kamu masih ingat lah. So I'm sure at that time you find it very headache to remember nak guna extent of reaction ataupun nak guna atomic balance. Okay. So this stoichiometric table is actually a much easier way to do mass balance for a reactive process. Kenapa saya kata senang? Asalkan kamu faham dia punya formula, and formula dia pun straightforward, senang je formula dia. Kamu tahu formula dalam table tu, kamu dah boleh buat mass balance terus for the entire process using this stoichiometric table. So that's why I say there's two purpose of learning it. First, nak tahu CA, CB dalam rate law. And the second reason is to teach you a much easier mass balance calculation using a form of table. Okay, right. So, but then nak belajar table ni pun ada juga dia punya perbezaan dia. Okay, to learn the table, you have two different types of table. Okay, why? Because remember kita belajar reaktor kita ada dua sistem, batch dengan flow. Batch tu batch reactor lah. Kalau flow tu CSTR, PFR. Okay, so table dia berbeza untuk batch system dengan flow system. Okay, tapi nanti kamu akan tengok perbezaan dia hanya cara kita mengira. Maksudnya kalau batch, saya guna number of moles. Kamu ingatkan kita pernah belajar kan kalau batch mesti number of mole, N. Kita guna N. Kalau flow system, kita guna molar flow rate. So, mole per time. So, kalau batch, mole. Kalau flow system, mole per time. Formula dia masih sama, just that pengiraan dia berdasarkan mole untuk batch, molar flow rate untuk flow reactors. Okay. Lepas tu, lepas kita dah buat table, kamu ingat kita buat table, lepas table tu baru kita akan find the concentration. So, table tu takkan memberikan kita concentration tau. Table tu hanya beri kita information dalam bentuk mole dan molar flow rate. Tetapi, from that table punya information, kita boleh guna untuk cari concentration. Okay, so kamu kena faham that step. Table is just to give you in the form of mole, molar flow rate. Then the value we will use to calculate the concentration. Okay, however, before I go there, let us learn first the table. Okay, so first of all, table dia. Okay, dia bentuk table lah kan. Okay, so dia ada column, dia ada row. Okay, dia akan ada 5 column. Ni 5. Patutnya 5 column. Okay, so the first column is for the species. So, setiap species in your system has its own row. So contohnya in this case, you have 4 compounds, right? A, B, C dan D. So each compound dia ada satu row dia sendiri. Okay. And if you have inert in your system, okay, walaupun dia tak terlibat dalam tindak balas, tapi dia ada dalam sistem kamu semasa reaction tu berlaku, it has its own row as well. So contohnya dalam kes ni, kamu tengok katakan ada inert, maka row yang kelima tu adalah row untuk inert. Okay, then last, so kolom pertama, kolom spesies, setiap satu baris untuk satu compound, termasuk kalau ada inert, satu baris juga untuk inert. Dan row yang terakhir adalah total. Kan kita nak buat mass balance kan, mesti ada total in, total out kan. Sebab tu bawah tu ada total. Okay, done. Now, next column, simbol. Okay, maksudnya macam ni. Katakan, you realise kan kadang-kadang dalam tindak balas, sometimes I will use the real chemical equation. For example, N2 react with H2 to produce ammonia, NH3. So, spesies dia akan jadi N2, H2, NH3. Simbol dia, kita tukarkan simbol dia kepada A, B and C, D. Sebab kan pengiraan kita kan based on A, B, C and D. So, if you are given the real compound, then you convert it into A, B, C, D. So, macam nak tahu nak convert, the easiest way, kamu ikut je lah sequence dalam chemical equation. So, chemical equation dia katakan N2 plus H2 produce 2NH3. So, N2 is your A, H2 is your B, NH3 is your C. So, kamu label ikut compound tu, kamu akan label simbol dia. Okay, so done the first 2 column. Okay, the last 3 column is always fixed. The third column is initial. Okay, apa maksud initial? Initial amount of each of the compound before the reaction takes place. Okay, again, initial column tu adalah untuk tahu berapa amount setiap compound before the reaction takes place. So logically kamu pun boleh fikirkan, so kalau initially mestilah hanya reactant dan inert jika ada yang akan ada nilai. Maksudnya produk pada waktu awal initially takkan ada sebarang produk. So initial untuk produk akan ada kosong, akan jadi kosong. Yang akan ada hanya untuk reactant and if you have inert. Okay, so that's the first. So basically initial tu adalah kamu punya in. Okay. Next column, change. Change ni to address berapa banyak setiap compound ni berubah semasa tindak balas. Again, the change column is to address how much each compound will change during the reaction. So naturally, your reactant will decrease, kan? Your product will increase. And inert, no change. Sebab inert tak akan berlaku sebarang perubahan dalam bilangan dia, kuantiti dia, sebab dia tak berlaku tindak balas. Means, quantity raw material berkurangan, quantity raw reactant will decrease, quantity of my product will increase. Okay, inert, no change. What about remaining? So kalau initial is the in, remaining mestilah yang out. So how much the amount remains after the reaction has taken place. Okay, berapa kuantiti setiap compound selepas tindak balas telah berakhir. So that's why you get your out. Initial is for your in, your remaining is your out. So kamu dapatlah actually the mass balance of the system of the reaction. Okay, now I explain in general. Now let's go specifically macam mana nak isi table ni. Okay, so bila saya ajar nak isi table ni, saya ajar dalam bentuk simbol sebab tak ada nombor lagi. Nanti bila kita ada contoh yang nombor, we will replace with numbers and you find it much easier with numbers. Kalau tengok simbol memang memeningkan. Okay, tapi I will still teach you. Okay, now imagine kita nak buat kolom yang pertama, kolom initial. Okay, kamu kena faham kenapa dia menjadi kompleks dalam table ni, sebab kita nak semua nilai dalam table ni hanya berdasarkan NA0 dan X. Again, I repeat, segala nilai dalam table ni hanya berdasarkan NA0 dan X untuk batch. Okay, before I forget, kita pergi batch dulu. Sorry, I skip a little bit, I go depan sikit. Kita start dengan batch kan? Okay, so kita start dengan batch. Segala nilai dalam table batch kita ni adalah berdasarkan bilangan mol. N, or in particularly is actually NA0 dan juga conversion X. So how do we do that? Okay, first of all, let's say now you have a reaction of which you have two reactant, two product. Katakan reactant saya A dan B dan produk saya C dan D. Okay, so saya dua reactant, dua produk. Okay, so saya nak kira berapa bilangan mol initially for each of the compound. So untuk compound A, species A, initial amount dia NA0. So contohnya katakan kamu tahu bilangan asam mol A adalah 5 mol. So NA0 sama dengan 5 or you just put 5 in the NA0 box, meaning NA0 tu 5 mol. Okay, done. Okay, so species A senang lah kan. Species B, okay, kita pun nak tahu how much is the initial mole of B. Tadi initial mole of A and A0. Now you want to know initial mole of B and B0. So NB0 is actually equals to NA0 theta B. Okay, so NA0 tadi yang kamu dah tahu kan, NA0 tu katakan 5. Tapi sekarang 5 ni kamu kena darab dengan theta B. So sekarang kamu jumpa satu lagi simbol. So as I said, memang banyak simbol kamu kena jumpa. The first symbol that you will meet is now theta B. Okay. Apa tu theta B? Okay, so simbol So theta B means berkaitan dengan B kan? Okay. The easiest way to explain what is B, sebab kalau kamu nak hafal formula dia memang susah. The easiest way for me to tell you how to remember apalah itu theta B. Theta B is the ratio of initial amount of B over initial amount of A. Okay, again is ratio of initial amount of reactant B terhadap reactant A. So kamu kena pasal dalam case ni and B not akan ada nilai sebab B ni kan reactant, so kita bilangan mol asal B ni kita akan tahu. Tetapi bilangan asal mol B ni boleh dikira berdasarkan Na0 multiply with theta B. Which I tell you theta B ratio amount B awal asal terhadap amount A asal. So saya cakap amount kan, so kenapa saya cakap amount? Sebab dia berjaya dalam bentuk yang berlainan depending on the question. Meaning to say, you can calculate theta B if you are given terus NB0 per Na0, boleh kira. Or you can also kira theta B if you are given initial concentration of B over initial concentration of A. Or if you are given in terms of mole fraction asal B terhadap initial mole fraction of A. Contohnya katakan dalam soalan this says, initially I have 60 mole percent A dan remainder dia mole percent B. So of course kalau 60 mole percent A adalah 40 mole percent B kan. So theta B akan sama dengan, theta B will equal to 0.4 over 0.6. Sebab YB0 0.4, YA0 0.6. So menggunakan mole percent ke mole fraction ke initial concentration ke initial number moles ke, asalkan dia adalah initial amount, kamu bahagi je dengan initial amount A, kamu akan dapat your theta B. Ataupun another example, katakan dia kata initially dia adalah equal molar of A and B. Apa maksud dia? Kalau dia kata equal molar of A and B, maksudnya 50 mole percent A, 50 mole percent B yang masuk initially. So meaning YA0 0.5, YB0 pun 0.5, 50%. So theta B is 1. Why 1? Because 0.5 divided by 0.5, you get 1. So that's how you calculate theta B. So bila kamu calculate theta B, katakan kamu calculate 1, kamu dah lah dengan Na0, katakan Na0 tadi was 5, right? So 5 times 1, 5. Ataupun katakan tadi kamu kira theta B kamu katakan 2, katakan 2. So 2 times 5 mole dapatlah 10 mole. Maksudnya NB0 yang masuk tu adalah 10 mole, Na0 yang masuk adalah 5 mole. So bila kamu kira, kamu ganti je 5, 10. So kamu dah tak, simbol tu hanya untuk tunjuk apa perkiraan dia, tapi sebenarnya kena ganti dengan nilai. Okay. Dan for B, okay, what about C and D? So C and D, in this example, C and D is product. Okay, so kamu dah tahu logik kan? So saya kata reaction engineering, many times kena fikir sikit logik. Logik can actually helps you a lot. No ni reaction. A lot of engineering courses the same. So kamu tahu C dan D tu product. So naturally awal-awal reaction takkan ada lah produk sebab dia belum terhasil tindak balas, right? So NC0 and ND0 is 0. They got no number of moles because they are not yet formed initially. So done. So next, inert. So inert ni tak semestinya kena ada. Dia bergantung kalau tindak balas kamu ada inert ataupun macam mana kita nak tahu ada ke tak ada inert. Kalau kamu perasan awal-awal sistem compound tu wujud dalam reaktor kamu, tapi kamu tengok dalam tindak balas dia tak ada pun. Tu maksudnya dia adalah inert lah. Means they do have in the system, just that they are not involved in the reaction. Tetapi dalam pengiraan mass balance ni mesti ada sebab dia compound yang masuk dia ada weight, dia ada mass. So regardless involved or not involved in the reaction, they are in the system, you have to calculate its amount as well. So we call it as NI0. So I stands for inert. NI0 means initial moles of inert pula. So berapa bilangan mole asal inert yang ada. So contoh paling senang lah, example-nya kalau tindak balas kamu melibatkan oksigen gas. Okay, katakan tindak balas kamu melibatkan oksigen gas, tapi as I told you, very rarely kita guna pure oksigen. Okay, biasa kita guna apa? Kita guna air. So kalau kita guna air, selain daripada oksigen, kita pun ada nitrogen, right? So the nitrogen is your inert lah. So basically katakan kamu nak buat stoichiometric table ni untuk case yang ada melibatkan air. So your I inert tu sebenarnya adalah nitrogen gas. So Ni naught tu adalah sebenarnya bilangan mol nitrogen. Okay, so that's an example that's easier for you to understand. So Ni naught sama dengan berapa? So Ni naught sama juga dengan Na naught multiply dengan theta I. Tadi theta B, sekarang multiply dengan theta I. So apa tu theta I? Kalau theta B was initial amount of B over A. Therefore, for inert, theta I will be initial amount of your inert over initial amount of A. So konsep dia masih sama. Kalau theta B, initial amount of B over A. Theta I, initial amount of inert over A. So let's say your inert is nitrogen gas. So you calculate your initial amount of nitrogen gas over your initial amount of your reactant A. So initial amount ni pun depends either mole fraction, concentration, initial number of mole. It depends on the question. It depends on what information provided to you. Either way pun nilai theta I tu will be the same. Okay, so contoh katakanlah case dia, let's say I give you your system, you have A, B and inert. Okay, let's say I tell you is 30% A, 30% B, then tinggal baki 40% inert. Mole percent mole percent. So maknanya dalam our system tu ada 30 mole percent A, 30 mole percent B, 40 mole percent inert. So berapa theta B? So theta B equals to 0.3 divided by 0.3 sebab YB naught divided by YA naught, 0.3 divided by 0.3, theta B is actually 1. Okay, what about theta I? So theta I will be equals to 0.4. Sebab tadi dia kata 40 mole percent kan? 0.4 divide by 0.3. YA naught was 0.3. So you get lah your theta I. So that's the calculation that you need to do to understand theta I and theta B. So when you get the theta I, don't forget multiply again with the Na naught. So katakan tadi kamu dapat theta I was 0.4 divided by 0.3 kan. So you multiply katakan dengan 5 mol. Dapatlah your theta I, dapatlah Ni naught punya nilai. So now you imagine initially tu kamu dah tahu Na naught, katakan Na naught 5 mol. And B naught let's say 10 mol. Okay, let's say Ni naught 7 mol, let's say, okay. So then what you do is the last column kamu kena kira total mol yang masuk. So total mole yang masuk kira saja 5 plus 10 plus 7. So you get let's say 22. So 22 mole total dia. So total mole tu kita guna N-T naught. Kenapa N-T naught? T is for total, naught is for initial, N is for number of moles. So initial total number of moles. So kamu kira. So kalau kamu faham, kalau kamu tengok macam simbol ni kompleks kan, tapi bila saya bagi nombor it's very easy, it's easier to understand. So NT naught 5 plus 10 plus 7, 22. So you write down 22 NT naught. NA naught 5, NB naught 10, and I naught 7. So NT naught double up, sum up, you get your NT naught. So done for initial. Now, next one. Okay, next one we go to the next table. The next table is for change. So tadi kita ada initial, right? Kita ada 3 column kan? Initial, the int. The next column is change. Okay, change ni kita nak tahu, kita nak kira sebenarnya how much each of this compound change during the reaction. Okay, again, change punya column ni to address berapa banyak sebenarnya setiap compound ni berubah semasa tindak balas. Okay, first. Second, maksudnya kalau ada perubahan, mestilah your reactant will decrease. Your product will increase. Maknanya compound yang menjadi raw material, compound yang reactant saya, mesti dia akan bilangan mol dia akan berkurangan. Sebab dia bertindak balas kan, dia akan consume. So bilangan mol dia akan berkurangan. Produk yang tadi kosong, sekarang bilangan mol dia akan bertambah sebab dia dah terhasil. Sebab tu, tapi berapa banyak dia terhasil, berapa banyak dia berkurangan. Ada formula juga. So formula dalam table tu akan menjadi minus for A, katakan konsep dia untuk A. Okay, A reactant, right? So it become negative or minus Na naught X. Inilah sebenarnya sebanyak mana A telah bertindak balas is actually equals to negative Na naught X. So contohnya katakan X kamu adalah katakan 0.8. Let's say X tu conversion kan. So katakan kamu tahu conversion. Conversion kamu 0.8. So tadi kamu ingat kan A kamu, Na naught kamu kan 5. Remember just now we do the table, Na naught was 5, right? So 5 multiply with 0.8 you get 4. So maknanya berapa banyak A yang bertindak balas? Sebenarnya ada sebanyak 4 mol yang telah habis bertindak balas. So itu konsep dia. Asal 5, change dia minus NA0 X. So NA0 X katakan 5, X is 0.8, you multiply, you get 4. Maknanya berapa yang telah bertindak balas? 4 mol. Okay. But most of the time, X tu kita tak ganti dulu dalam table tu. X tu adalah unknown yang kita biarkan dahulu. Sebab X tu ialah bergantung kepada kita punya reaction, right? So X tu normally we leave it as it is. So that's why it become minus 5x. Katakan NA0 is 5. So it become minus 5x. So if you are given conversion, you replace the conversion. If you're not given the conversion, you just leave the x as it is. So it become, let's say, minus 5x. Okay, so that's for A. For B, okay, sebab tu saya kata table ni susah sikit tapi dia ada formula. So kalau nak buat mass balance, me personally, saya rasa table ni lebih senang nak buat mass balance sebab dia ada formula dah sebenarnya. Okay. For B, ada formula juga. Okay, kamu kena ingat dalam this example, B is a reactant. Okay, I have to keep emphasizing B in this example is reactant. So B will also consume or B will also decrease. So how much the decrement or how much it decrease? It is minus B per A and A0 X. So tambah satu lagi benda. B per A itu apa? B per A adalah stoichiometric coefficient in your chemical equation. So B is for the number in front of species B in the chemical equation. A is for the number of the species A in the chemical equation. So, kamu kena tengok balik chemical equation. B per A itu berapa? So, katakanlah contohnya, let's say the reaction is 1A with 2B. So, B per A dia adalah 2 per 1. So, jangan lupa negatif tu ada. So, negatif 2 per 1 multiply with NA0. Let's say 5. Kan tadi kita kata NA0 kita 5. So, kali dengan 5. Katakan X kita tak tahu. So, biarkan. So, become negative 10X. Let's see. Katakan B per A itu 2 per 1 time with NA0 5. So, you get 10, right? So, negative 10X for your change of B. Itu adalah berapa banyak B kamu berubah. Okay. What about C and D? So, C and D in this example are products. So, product, dia konsep dia kalau kamu confused lah, negatif, positif, kamu just ingat je. Kalau benda tu reactant mesti negatif, kalau produk dia mesti positif. Senang, that's the easiest way to not get confused. So for your product akan menjadi positif. So positif, how much? Kalau C become positive C per A and A0 X. So the C per A is your stoichiometric coefficient again. So now you look pula kat compound C, berapa dia punya stoichiometric coefficient. Bahagi dengan compound A punya stoichiometric coefficient, you multiply with NA0 X. So same dengan D pun sama. So again positif juga. Dan positif D per A, okay, multiply with the NA0 X. So katakanlah C per A tu 1. So 1 darab dengan 5, NA0 5 darab dengan X. So jadi positif 5X. Positif tu kalau nak tulis pun boleh, tak tulis pun tak apa. Tapi kalau kamu takut kamu confused, kamu tulislah positif tu untuk senang untuk kamu ingat. So same for D as well. Katakan D per A tu adalah 1 juga. So 1 times 5. So become D tu pun change dia 5X. Let's say for C change dia pun positive 5X. D pun positive 5X. Okay, done for the column change. You don't need to find the total change. Sebab total balance hanya initial in dengan total out yang remaining. Yang change tu tak payah cari total. No total, you don't need to find the total for the column of the change. Okay, but before I forget, what about inert? So again, logic lah kamu kena ingat. Inert, let's say nitrogen gas in your reaction. Kamu tahu nitrogen gas ni ada dalam sistem. Initially kamu kira nilai dia. Okay, change, kamu tengok dia tak terlibat dalam tindak balas because dia tak ada dalam bersamaan tindak balas. Therefore, the change mestilah tak ada change for inert. Okay, so let's say lah kamu masih fikir yang kamu kena letak nilai. Kamu maybe although you know it's a inert, but at that time you are stressed, you still want to find the nilai. Okay, you want to put the change for the inert. Okay, just think logically. Kalau nak cari nilai for inert, kamu kena tahu stoichiometric coefficient kan untuk inert. So kamu tahu kalau inert takkan ada stoichiometric coefficient sebab dia tak ada pun dalam persamaan tindak balas. So tak ada dalam persamaan tindak balas, tak ada stoichiometric coefficient, definitely lah tak ada change for it. So that's another way for you to realize, okay, kalau kamu nak buat pun sebenarnya kamu tak boleh buat sebab there won't be a stoichiometric coefficient for the inert in the chemical equation. Okay, so done for the change. Okay, remaining. Sebenarnya remaining yang paling senang. Okay, initial dengan change ni saya admit kamu kena hafal sikit formula. Okay, remaining kamu tak payah hafal. Okay, remaining is very simple one. Okay, but before I go to that, remaining is the out. Initial in kan, so change berapa yang berubah, remaining is berapa yang tinggal selepas tindak balas. So kamu perasan, kalau initial untuk A, initial and A not. Kalau remaining NA lah, NA not initial number moles. NA remaining ataupun berapa mole yang tinggal selepas tindak balas. So how do we find NA? So NA equals to, kamu buat apa? Kamu copy sahaja initial NA not. Kamu copy yang change minus NA not X. Kan kamu nampak NA sama dengan NA not initial minus NA not X. Your change. Dapatlah your remaining. Done. So kalau kita nak bracket kan, kita nak keluarkan NA not, kita bracket kan, you will get equals to NA not in bracket 1 minus X. Done. So that's to do for remaining. Remaining sebenarnya kamu copy je initial, kamu copy je remaining, kamu combine, kamu dapat kamu copy initial, kamu combine with the change, you get your total, you get your remaining already. Kamu copy and combine, kamu dapat your remaining. Okay, so let's say we go for the second one for B. So kalau initial B and A not and B not, remaining B and B. So NB equals to, copy je NA not theta B combine dengan minus B per A and A not X. So you get your NB. So again, I will take out NA not sebab dua-dua tu ada NA not kan. Kita take out NA not dalam kurungan in bracket becomes theta B minus B per A X. So sekarang kalau kamu perasan, kamu dapat perkaitan dalam table kamu sebenarnya semua dalam bentuk NA not X. Ada sikit theta, ada sikit stoichiometric coefficient. Tapi basically semua dalam bentuk NA not dan X. Okay, what about C? So C and C. So and C lagi senang because we don't have remaining, we don't have initial for C because initially C is a product, C and C not is 0. So your remaining of NC sebenarnya sama dengan your change only. So plus C per A and A not X. So D the same. Initial we don't have, we only have the change which is D per A and A not X. So your ND equals to plus D per A and A not X. So kamu bayangkan, I'll give you example in form of number. Katakan NA not tu 5. Tadi kita dapat kan NA not 5. NA not X minus 5X, right? So by right, NA sama dengan 5 minus 5X. Ataupun katakan we know the value of X. Tadi saya beri contoh katakan X 0.8. Hence minus NA not X jadi minus 4, right? So 5 minus 4 tinggal 1. Maksudnya 5 yang masuk, 4 yang telah bertindak balas, dia saja jadi negatif 4 yang telah bertindak balas, yang tinggal adalah 5 tolak 4, 1. So NA is 1 in the form of number. In the form of symbol, jadilah NA not in bracket 1 minus X. Okay. So inert pula, inert terbalik. Inert, initial ada, change tak ada. So inert become, remaining inert samalah dengan initial inert. Logic lah because inert is that won't have any change. So how much they enters is exactly how much they remain after the reaction. And then subsequently you have to calculate the total remaining. Kan mass balance, total in, total out. So you calculate the total out. So kamu jumlahkan sahaja berapa jumlah remaining, you total up, you get your total remaining. So basically what you do in this table is the entire mass balance for a reactive system. Sebenarnya kamu belajar atomic balance, kamu belajar extent of reaction. This is another alternative using a table dengan ada formula. Okay, now done. I'm already done on the table. But now kamu kena faham which the part that sometimes student jadi confused. Kenapa? Sebab tadi I address when you have two reactant. Okay, reactant A, reactant B. Okay, tapi kamu ingatkan kadang-kadang dalam tindak balas ada satu reactant kan, rarely kita guna 3 reactant lah. Tak kata tak ada, ada je tindak balas sampai 3 reactant. But usually 2, most common one. Or sometimes you only use 1 reactant. So katakan dalam case di mana reactant adalah 1. Okay, so kalau sekarang reactant 1, A is your reactant, masih sama kan? Tetapi sekarang kalau satu reactant dia ada 2 produk kan? Sekarang dalam case ni B tu dah jadi produk. Do you understand? Sebab sebelum ni case dia A tambah B hasilkan C dan D. Tapi kalau dia satu reactant, B tu sekarang dah jadi produk, right? So the table will be different for the case of B. Kes A, kes C, kes inert masih sama sebab dia masih reactant. C masih produk, inert masih inert. Tetapi untuk B dia dah berubah because the previous example, I took B as a reactant. In this example, B now is my product. So what happens to the stoichiometric table? Okay, so apa yang berlaku? In the case of initial amount of B and B naught dah jadi kosong. Dah bukan NA naught theta B. Kenapa? Sebab B tu adalah produk dalam example ini. Ataupun dalam case ini, senario ni, B is no longer a reactant, B is the product. Okay. But let's say lah kamu get confused juga lah. Okay. Sebab kadang-kadang I know you learn a lot, you get confused. You remember, okay, NB naught tu mesti NA naught darab dengan theta B. Let's say kamu remember NA naught, NB naught ni mesti sama dengan NA naught darab dengan theta B. Okay, lepas tu kamu ingat pula. I told you right, theta B nak kira mesti initial amount of B over A. Dia mesti, formula dia mesti nak kira theta B, initial amount of B over A. Then you realise, untuk senario tu, kamu takkan ada initial amount of B. Sebab B product kan. So kamu tinggal tengok, kenapa tak ada initial amount of B? Sebab B is a product. So if you cannot calculate theta B, teruslah kamu tak boleh kira NB naught. So maksudnya NB naught tu adalah kosong. Okay, so that's another way. If let's say you really got confused, that's another way. Kamu tahu tak ada initial amount, tak boleh kira theta B, tak bolehlah kira NB naught. So memanglah NB naught tu kosong sebab B is a product. So that's the part. So what about the change? Change pun dah berubah. Tadi when B was a reactant, it become negative B per A and A naught X. Because B was a reactant, it will decrease. However, when B is a product, in this reaction, katakan sekarang B is a product, it become positive B per A and A naught X. Because B is now produced during the reaction. So then what about your NB, your total, your remaining for B and B? So number most remaining for B become plus B per A and A naught X. It's only the change. Initial dah kosong kan, so just the change. So NB equals to plus B per A and A naught X. So this is the only difference in the table when you have the previous case of which you have two reactants, and in this case where now you have one reactant and B is now a product rather than a reactant. Okay, so done. So again, if I forget, okay, yang saya ajar kamu dalam bentuk table ni adalah bentuk simbol. Okay, tapi bila kamu solve the real question, dia adalah dalam bentuk nombor. It will be the form of number. So means the whole table tu, you will replace with number. Jangan just biar simbol. Dah ada nilai, kita ganti dengan nilai. So later we will attempt one question. You will see how does this happens. Okay, so done. So now let us go in. Okay, kamu dah buat table habis. Okay, we are done on the table. Tapi kamu ingat saya kata tadi, kenapa kita buat table tu? Satu, sebab mass balance. Kedua, sebab kita nak tahu concentration. Sebab rate law ada concentration. CA, CB. So sebenarnya, we want to use the stoichiometric table to find CA and CB. Dan juga, if you want to find CC, you want to find CD, you want to find CI, you can actually find using the stoichiometric table. Okay. However, nak cari concentration ni pula, ada sedikit dia punya rules. Okay. What do I mean by that is because, alright, in the case of batch, okay, so dalam case dalam batch reactor, table tu, bila kamu nak buat, dia sama je. Untuk liquid, gas, table masih sama. Okay. However, dan juga, when you want to find the concentration, okay, bila kita nak cari concentration, the same concept is applied. Meaning, for gas dengan liquid pun, concentration dia adalah sama untuk case batch reactor. So again, I repeat, in the case of batch reactor, regardless kamu buat liquid or you buat gas, your compounds, the table and the concentration are the same. Okay, so nanti kenapa saya cakap benda ni? Sebab nanti kalau kita buat, when we do for flow reactor, dia dah tak sama. Dia ada beza untuk gas dengan liquid. Sebab tu yang menjadi a bit confusion untuk student. Kalau batch tak kisah fasa dia. Tapi kalau flow, kita dah kena kisah fasa dia. So that's the challenge lah. But until now, until so far, you just remember kalau batch reactor, regardless fasa dia, both table and concentration are expressed the same. Okay, why is expressed the same for the concentration for batch reactor? It's because Ingat tak, dulu saya ajar kamu, kalau batch, we are referring to the volume. Kalau flow, kita refer kepada volumetric flow rate. Okay. So untuk volume reactor ni, regardless kamu guna liquid ke, kamu guna gas ke, volume reactor kamu tak berubah. Meaning before reaction, after reaction, your reactor volume remain constant. So maksudnya V equals to V0. Initial volume of my reactor equals to the outlet volume of the reactor. Or erti kata lain, initial volume dengan remaining volume reactor adalah sama. Sebab reaktor kita tak expand, tak shrink, takkan mengecut. So volume reactor adalah sama. Okay. Kenapa ni adalah penting untuk tahu? Okay. Now, kita express concentration. Okay. At this moment, kita akan guna table ni untuk express concentration. Okay. So, tetapi at this stage mungkin kamu akan rasa expression tu banyak, which is true. Tetapi later as you go to chapter 4, chapter 5, chapter 6, you will always see this equation that kamu dah akan terus automatically memorize equation dia. Apa maksud dia? Okay. Now, I want to find, remember I told you kita check concentration kan? Kita check concentration A, concentration B, concentration C, concentration D. Concentration yang remaining selepas tindak balas. So, concentration of A naturally equals to CA equals to NA over V. Kan concentration kan mole per volume. Katakan contoh unit dia mole per dm cube. Dimension dia mole per volume. Sebab tu saya kata kadang-kadang daripada unit tu kamu dah boleh agak formula dia. Macam concentration kamu tahu unit dia mesti mole per liter, mole per dm cube. So kalau tukar kepada bentuk dimension, mole per volume. Sebab tu dia akan menjadi bilangan mole A and A over volume reactor. Okay. Now, this is why we do the table. Sebab daripada table, kita tahu remaining untuk remaining untuk A, NA equals to NA0 1 minus X. Daripada table tadi kita buat tu, kita dah dapatkan dalam bentuk ni. So, I replace my NA with NA0 in bracket 1 minus X, close bracket, which I obtained from my table. Okay, then bottom. Okay, now, disebabkan we know that the volume of reactor initial and remaining is the same because our reactor does not shrink, does not expand, then we can replace V, the remaining volume, with initial volume. Okay, now I definitely you will wonder kenapa nak buat ni? Sebab if you realize now, kalau saya ada NA0 kat atas, saya ada satu V0 kat bawah. If I divide NA0 with V0, what do I get? I get CA0. So now instead of becoming NA0 1 minus X over V0, now I get the NA0 per V0 as CA0. Dalam bracket tu masih 1 minus X. So now I already express concentration of A, remaining concentration of A in the form of CA0 in bracket 1 tolak X. So to get this, yang kita kena gunakan stoichiometric table punya information yang mengatakan bahawa NA equals to NA0 1 minus X. That's why I told you why we learn the table is because we want to learn to express the concentration. Okay, so you don't have to worry. Mungkin ada stage kamu tengok nak express tu panjang. Tetapi nanti bila chapter 4, chapter 5, chapter 6, kamu guna balik CA sama dengan CA0 1 minus X. Kamu akan guna banyak kali that you automatically will terus remember CA sama dengan CA0 in bracket 1 minus X. Okay? Right. So again, concentration ni regardless liquid atau gas, you are expressing the same way. Because liquid atau gas, dia punya volume reactor takkan berubah. Okay, next I will go to B. Okay, so untuk reactant B, saya nak express pula reactant B. So reactant B, of course saya kena jadi CB. Tadi CA, kalau reactant B, CB. So CB equals to number moles of B over reactor volume. Logik lah, kalau saya nak tahu berapa kepekatan B, mestilah bilangan mole B terhadap volume reactor. So kalau macam sikit otak kamu, nak tahu kepekatan B, kena tahu berapa bilangan mole B bahagi dengan isi padu reaktor. Okay, then pula kamu pun belajar daripada table. Tadi dah buat table kan yang panjang-panjang. Table kata NB equals to NA0 in bracket theta B minus B per AX. Tadi yang table tu kan saya dah kurungkan. I take out from the box. So we express NB equals to NA0 in bracket theta B minus B per AX. So I replace now my NB with the one that I obtained from the table. So at the top become Na0 in bracket theta B minus B per AX divide by volume reactor tu remaining volume reactor saya jadikan sebagai V0, initial volume of the reactor. Ni bukan kita nak buat sebarangan sebab kita memang tahu dalam batch reactor volume doesn't change. And kenapa kita nak ganti? Sebab kalau saya ada Na0 di atas, saya ada V0 di bawah, dia boleh menjadi Ca0. So konsep dia kalau kita ada Na0 kat atas, V kat bawah, kita tak boleh jadikan dia Ca0. Dia mesti not, then become not. So mesti Na0, V0 jadi Ca0. Sebab tu V tu kita jadikan V0. And although we turn the V to V0, we don't simply turn it because we have an understanding volume reactor tak berubah. That's why the V can become V0. So kamu kena faham mathematics in chemical engineering, the mathematics is not changed sesuka hati. It changed according to the scenario or according to the phenomenon explained by the chemical engineering. Okay, sebab tu V jadi V0, then now it becomes Ca0. So dalam bracket tu it still remains so theta B minus B per AX. So now tadi you express Ca, now we have express for Cb. Okay, so again kenapa kita nak express ni? Sebab dalam rate law kita kan ada Ca, Cb kan. So sekarang kita dah tahu Ca kita dalam bentuk Ca0 1 minus X. Cb in the form of Ca0 in bracket theta B minus B per AX. So next one is bila case when B is your product. Okay, kes yang pertama bila B adalah reactor. Ingatkan tadi kita ada dua table kan? Sebab table pertama, I told you when B is a reactant. Table kedua kan dah berubah B tu sebab B adalah product. So when the table change, the concentration pun is already different. It cannot be the same sebab the table tu dah berubah. And B tu kita dah express differently. So for the second case, so it become CB, outlet remaining concentration of B equals to remaining moles of B over reactor volume. Okay, so remaining mole of B for the case where B is a product, it become B per A Na0 X. Sebab tu it become plus B per A Na0 X. I divide by V0 again. Kenapa saya jadikan V kepada V0? Sebab then saya boleh Na0 top divide by V0 bottom, I get Ca0. So now my Cb equals to plus B per A Ca0 X. Maksudnya kamu tahu schematic coefficient, kamu tahu Ca0, kamu tahu X, kamu dah boleh cari Cb. So kamu kena tengok, you can see concentrations of B is expressed in two different ways depending on whether your B is your reactant or your B is a product in the reaction. Okay, so done on B. Okay, now we go to C. Okay, so B dah done kan? C. Okay, C sama je konsep. Inert pun sama je konsep. Kita just ambil kalau C, mole of C, remaining moles of C divided by the volume of reactor. I take from the table and C is equal to C per A Na0 X divided by volume reactor. I change from initial become from remaining volume become initial volume. I divide top and bottom. I get Cc, concentration of C, remaining concentration of Cs plus C per A Ca0 X. For D, the same. So concentration of D become remaining concentration of D become plus D per A Ca0 X. Okay, so kita tengok macam sama kan? Just that satu C per A, satu lagi D per A. Then the last one for inert, the same. So inert concentration remaining equals to remaining moles of inert divided by remaining volume or the outlet volume. From the table, initial moles of remaining moles of inert is Na0 theta I divide by the initial volume of the reactor, you get the concentration as Ca0 theta I. So although sebenarnya table tu digunakan untuk express A dan B sahaja, but you can also use a table to express for the other compound. So kenapa kita nak tahu ni? Kita nak tahu ni sebab kalau kamu katakanlah kamu dah ada produk kan, okay, kamu nak tahu kepekatan dia. You basically kalau kamu dah tahu Ca0 dan X, kamu boleh kira kepekatan untuk semua compound. If you realize, if you have Ca0 and X, you know your initial concentration, you know your conversion, you can calculate the remaining concentration of A, B, C, D and even inert if you have inert. Okay, so That is actually why you learn stoichiometric table. Okay, so I will do one example, then we are done for today because I don't want to go to the flow one. The flow one is a bit complex. Flow one I will continue the next lesson. We do one example, we are done for today. Okay, so the first example, the production of ammonia gas, okay, NH3 can result from the reaction of nitrogen gas with hydrogen gas. So the reaction is N2 plus 3H2 produce 2NH3. So dah when you go to chapter 3, you must be really careful of the chemical equation, especially the stoichiometric coefficient. Jangan lupa nombor di hadapan spesies tu dalam persamaan kimia is very important. Okay, next dia kata the isothermal isobaric. Okay, so sebelum ni mungkin kamu belum pernah tengok ayat ni. Iso means same, thermal means heat or means temperature. Means in the reaction there's no change of temperature. Isobaric means constant pressure. Okay, means dalam case ni, dalam reaction ni, dia adalah they got no change of temperature, they got no change of pressure. Okay, irreversible reaction. Okay, initially consists of 60 mole % hydrogen and the balanced nitrogen gas. Okay, so dia kata initially dalam kes ni, saya ada nitrogen, tidak bahasa nitrogen gas dengan hydrogen gas kan. So dia kata initially ada 60% hydrogen gas and of course balanced nitrogen gas tu adalah 40% lah, mole percent. Meaning, kalau kamu perasan, okay, N2 adalah your A, hydrogen is your B. Kita ikut susunan dalam persamaan kimia. So yang dibagi 60 mol persen ni adalah hydrogen. Hydrogen dalam soalan adalah your B. So sebenarnya dibagi YB0 0.6. So again I repeat. Dia kata 60 mol persen hydrogen gas. Dalam in this reaction, nitrogen is your A. Nitrogen gas is your A. Hydrogen gas is your B. So the 60%, 60 mole percent is actually your YB0, which is 0.6. Initial mole fraction of B, which is hydrogen gas, 0.6. So naturally, Ya0, your initial mole fraction of nitrogen gas is 0.4. So YB0 0.6, Ya0 0.4. Carry out in a 20-liter batch reactor. So, apa tu liter? Liter dimension dia volume. So, volume reaktor kamu 20 liter. Your V, your big V is 20 liter. 20. Okay. With 10 molar of nitrogen gas. So, what is this 10 molar nitrogen gas? So, I hope you still remember M. The big M is molarity. Molarity is concentration. So 10 molar is actually 10 mole per liter. Apa tu 10 mole per liter? Mole per liter is dimension dia, mole per volume is the concentration. Concentration of what? Kamu kena pasal juga. Dia kata concentration of nitrogen gas. Nitrogen gas adalah kamu punya A. And then dia kata carry out in a batch reactor with 10 molar of nitrogen gas. Maksudnya that is your initial concentration of your nitrogen gas, which is your A. So your Ca0 is 10 mole per liter. Molarity tu mole per liter atau mole per dm³ pun sama. So your Ca0 is 10 mole per liter. So kalau kamu perasan dalam kes ni, dia bagi kamu Ya0, YB0, dia beri volume V, they give you Ca0. Okay, so that's all for information that you have, right? So N2 must be used as the basis for all calculation. Okay, apa maksud ayat ni? Maksud ayat ni sebenarnya, dia kata N2 is the basis for all calculation is actually to tell you N2 is your A dalam kamu punya pengiraan. So kan sebenarnya saya kata kita nak kena tahu kan mana satu A, mana satu B kan. So biasanya one, the first compound in the sequence is your A. Ataupun dalam soalan ni diberitahu lagi sekali lagi. Dia kata N2 digunakan sebagai asas pengiraan. Meaning your N2 is your A in the calculation. So the question wants you to construct a stoichiometric table. So all values should be in the form of conversion only by numerically evaluating all other symbol. Example, epsilon, theta. Apa maksud ayat ni? Maksud ayat ni adalah they want us to do a table of which the entire table is in the form of numbers except for your x. Sebab tu dia kata in the function of conversion x. Maksudnya setiap simbol lain dalam bentuk nombor kecuali x sahaja yang kita biarkan. Kita tinggal dalam bentuk x. Okay? Sebab kita tak diberi nilai x untuk part A. Then part B, baru kita cari outlet concentration for all species. If the conversion is given as 40%. Dalam part B, part A disuruh kita buat table, part B disuruh kita cari the concentration dan dia baru beri kita nilai X untuk part B. Sebenarnya part A, X tu kita tinggalkan, kita biarkan as X. Part B only we substitute the X with 0.4. So how do we do the table? Okay, so sebelum kamu ingat nak buat table ni, most of the time student punya mistake is at the very first line dia dah buat salah. Apa maksud dia? Okay, kamu kena ingat kalau stoichiometric table, okay, kalau batch, dia punya nombor tu dalam bentuk bilangan mol or more exact dalam bentuk Na0. So means kalau selagi kamu tak tahu Na0, you cannot do the table. So contohnya tadi dalam soalan dia beri kita Ca0 kan, yang 10 mol per liter tu Ca0. Katakan kamu tak tahu ataupun kamu tak ingat ataupun kamu salah, kami ingatkan yang 10 mol per liter tu adalah Na0. So when you do that mistake, the entire table is already wrong. So means the entire table you will get 0 marks because of the very first understanding yang kamu salah, yang kamu ingat 10 mol per liter tu adalah Na0. Tetapi sebenarnya bukan. 10 mol per liter tu adalah concentration Ca0. You replace with the wrong understanding, the entire table you get 0 straight away. Or basically the entire question dah kosong at the very first line kalau kamu salah pemahaman. Okay, that's why I keep repeating about it. Okay, so in order to do the table, kamu kena tahu dulu Na0. Selagi tak tahu Na0, tak boleh buat. Okay. So in this question, they don't give us Na0. However, they give us Ca0 and they give us volume. So hopefully you still remember ada perkaitan dia. Na0 ataupun perkaitan dia sebenarnya adalah Ca0 sama dengan Na0 per V0. Okay, itu perkaitan dia. Ca0 sama dengan Na0 bahagi V0. So kalau kita nak cari Na0 sama dengan Ca0 multiply with V0 lah. Ataupun kalau kamu tak sure darab ke bahagi, kamu confused, buatlah pembatalan unit because you know Ca0 10 mol per liter. So if you multiply with volume 20 liter, kamu perasan my liter can be cancel. I'm left with mol. So kita nak cari bilangan mol kan. If your unit is mol, most likely betul lah jawapan kamu. Tapi katakan kamu cancel, kamu dapat liter bermol. Ataupun kamu dapat liter. So kamu tahulah mesti salah sebab bilangan mol mestilah mol. Selagi tak dapat mol, tengoklah balik pengiraan dia. Okay, so now you get your Na0. Okay, second thing. Okay. Okay, tak apa, kita start dulu table lah. Nanti kamu confused, kita start dulu dengan table. Okay. So dalam table ni, kamu kena ingat, we only have in the question, we only got 3 compound. Nitrogen, hydrogen gas, ammonia. There's no other gas mentioned. Kalau kamu perasan, dia tak cakap pasal apa-apa compound lain, dia tak cakap. Hanya ada nitrogen, hydrogen, ammonia. That's why you only have 3 rows. So first row is for nitrogen gas, second row is for hydrogen gas, third row is for the ammonia. Okay, so that's why nitrogen gas, species dia, simbol dia A. Hydrogen gas, simbol dia B. Ammonia, simbol dia C. So kita dah ikut susunan dia. Okay, so we do first for nitrogen gas. So initial nitrogen gas, Na0 equals to 200. We calculated, right? Na0 200. So Na0 equals to 200. Change. So the change for nitrogen gas, formula dia adalah minus Na0x. So already given. Formula dia minus Na0x. So my Na0 is 200. My x is unknown. So it become negative 200x. So yang mol tu kamu dah tak payah tulis sebab mol tu dalam the first row kamu dah terus label. Initial change dengan remaining tu kamu terus label dalam kurungan mol. So kita tahu dalam semua pengiraan ni dalam bentuk mol. So it become the change for A for nitrogen gas is negative 200x. So what about the remaining? So the remaining Na technically equals to what? Na technically equals to, kamu copy je, 200 minus 200x. So you get belakang dia, 200 minus 200x. So kamu remaining kamu tak payah hafal. You don't need to memorize anything. You just know remaining Na equals to combine your initial 200 with your change minus 200x. Done. So next for hydrogen gas, your B. So for your B, kita nak cari MB0, initial moles of hydrogen gas. Tadi yang 200 tu adalah initial mole of nitrogen gas. So kita nak cari sekarang initial mole of hydrogen gas. So initial mole of hydrogen gas NB0 is equal to theta B and A0. Okay, so first nak kena cari theta B. Formula kata kena theta B darab NA0, right? So and theta B, how to find? So theta B equals to, if you remember, initial amount of B over A ataupun initial amount of hydrogen gas over initial amount of nitrogen gas. From the question, the only initial amount dia bagi was the mole fraction. We know initial mole fraction of hydrogen gas was 60%. Initial mole percent of nitrogen gas was 40%. So YB0 0.6. Yang ni pun kamu jangan confuse. Kadang-kadang soalan student confused. YB0 yang mana satu, YA0 yang mana satu. Dalam soalan ni saya beri YB0. I ask you to find YA0. Sometimes in question I give you YA0. You have to find your YB0. So kamu kena betul-betul faham soalan. What information is given? Adakah itu adalah B ataupun itu adalah A? Okay, so when you calculate correctly, 0.6 divided by 0.4, you got your theta B 1.5. So 1.5 theta B multiply with your NA0 200. So tadi NA0 kita dapat 200, right? You multiply with 1.5, you get 300. So apa maksud 300 tu? Maksudnya bilangan mol B yang masuk adalah 300. Itu je, paling senang. Bilangan mol A yang masuk 200, bilangan mol B yang masuk 300. What about the change? So in this case, B is a reactant. Hydrogen gas is your reactant. Hydrogen gas will decrease, right? So it become minus B per A. Jangan lupa dia adalah minus B per A. So tengok dalam chemical equation, formula dia kan minus B per A kan. Dalam chemical equation, the B is 3, the A is 1. So minus 3 over 1 times NA0X. So formula dia was minus B per A NA0X, right? So B per A is 3. Don't forget 3 over 1 sebenarnya. Tapi kamu tahu per 1 kita tak tuliskan. So, jadi minus 3 multiply with NA0X. NA0 200. Just now we got already NA0 is 200. So 200 multiply with 3, you get 600. So it become negative 600X. So that is the change for B, which is negative 600X. Then you get your NB, your remaining for B. So your remaining for B and B equals to, again, just combine your initial 300 combine with your change negative 600x. So it become NB 300 minus 600x. Done for B. Okay, last one for C. So for C, initially C ammonia product. You don't have initial moles. So the initial for C, 0. Okay, what about change? So for ammonia, it's a product. Positive is formed. So plus C per A and A0X. Again, C per A adalah stoichiometric coefficient dia. So kalau kamu tengok dalam persamaan kimia, the C number, the in front for C is 2, ammonia 2, A dia 1. So become plus 2 over 1 multiply with NA0 200 multiply with X. So you get 400X. Nak tulis positive 400X pun boleh. You want to write 400X also is fine. So your remaining for your C and C, bilangan mol yang baki tinggal adalah sama dengan 400X. So tengok, saya kadang tulis negatif, kadang-kadang saya tulis positif, kadang-kadang tak tulis. Tak purpose sebenarnya untuk positif. Negatif you have to write. The positive one is okay if you don't write. Okay, then don't forget, you're not done yet because you have the last row, total. So how much total initial? So kamu kena kira, total initial is NT0. So kamu kena kira NT0 kamu. So NT0 kamu sama dengan, you just add all the initial, meaning 200 plus 300 equals to 500. Done. So maknanya bilangan mol asal yang masuk total dia adalah 500 mol. Okay. What about remaining? Remaining part ni kadang student jadi confused sebab remaining ni ada X, ada nombor kan. So kalau kamu ingat pengiraan ni, kamu kena nombor tambah dengan nombor, X tambah dengan X. Contohnya dalam kes ni, total remaining is NT sama dengan 200 minus 200X plus 300 minus 600X plus 400. So nombor tambah dengan nombor, so kamu buat 200 plus 300 is 500. X dengan X kamu kena tambahkan. So maknanya jadi negative 200X plus negative 600x. Kalau negatif dengan negatif, kamu dapat negative 800x. Plus 400x, you get negative 400x. Sebab tu jadi total remaining NT sama dengan 500 minus 400x. So yang part remaining kerana sudah akan buat salah, just remember number I add with number, the x I add with x. So done for the table. So kalau kamu perasan, table tak susah when you replace with number. However, there are tendency to do mistake kalau kamu ganti dengan nilai yang salah. For example, like I told you, kamu sepatutnya kena kira NA0 dulu. Katakan kamu tak kira, kamu terus guna CA0, the entire table is 0. The remaining of the question also will be 0. Okay.
Doktor,
Yes, yes.
nak tanya sikit.
Boleh.
Kalau contoh kan, yang dekat NB tu, yang kotak kedua H2 tu. Kalau kita tak tulis equation yang depan tu, terus tulis 300 tolak 600x.
Untuk NB ke? NB, yes. Kamu terus tulis NB sama dengan 300 tolak 600x pun okey. Contohnya macam
Okay.
depan pun NB0 kamu terus tulis sama dengan 300 pun tak apa.
Okay.
Simbol tu saya letak, tapi dalam kamu punya penyelesaian you don't need to put. The important is actually the numbers, not the symbol. However, I do advise to put the symbol sebab katakan kalau nombor kamu salah, kamu ada letak simbol, you still can get some marks for the symbol. Tu masalah dia. Kalau tak letak simbol, nombor salah memang dah tak ada markah langsung. But if you put the symbol, although your number can be wrong, you might get some marks for putting the symbol. So ada pro and cons lah. Dia akan memakan masa, but it might save you a little bit of marks if you put the symbol. Okay? Alright. So thank you for the question. Thank you. Okay, so the last one for today, before we finish, we want to express the concentration. So ingatkan kita belajar panjang-panjang buat table ni, sebenarnya kita nak cari concentration. Kita nak cari concentration A, concentration nitrogen gas, hydrogen gas and ammonia. Okay, so from the equation, so kamu tahu concentration of A equals to number moles of A over volume reactor. Okay, so daripada table, sebab tu kita buat table, daripada table kita tahu number moles of A is 200 minus 200x. So I replace NA sama dengan 200 tolak 200x. Volume reactor saya ganti dengan 20 liter. Kita tahu kan daripada soalan, the volume of reactor was 20 liter. I replace my X with the conversion. Dalam soalan B, dia told us the X is 0.4. So I replace my X with 0.4. I calculate, I get my Ca as 6 mole per liter. Dan sebab tu kita perlukan table sebenarnya. Table tu beritahu kita nilai Na. So kita dapatlah nilai Ca. Same for Cb. So Cb jangan pula guna Na. Kalau Cb mestilah Nb over volume of reactor. Okay. So mungkin kamu terfikir kenapa volume tu satu volume je, tak ada volume A, volume B, volume C. Sebab volume ni merujuk kepada volume reactor. It doesn't refer to the volume of your compound. It refers to the volume of your reactor. So then you take from the table, NB is equal to 300 minus 600x. Replace the X with 0.4, replace the volume 20 liter, you get the concentration 3 mole per liter. Maksudnya, kepekatan A selepas tindak balas is 6 mole per liter. Kepekatan B selepas tindak balas was 3 mole per liter. And lastly, for your ammonia, again take from the table, the remaining moles of C is 400x. You replace X with 0.4, you replace your volume with 20, you get the concentration of your ammonia as 8 mole per liter. So I think that's all for today. Okay, I will not go to flow system because flow system is another headache. So I'm done for today's class. So on Wednesday, we will complete a little bit of the tutorial question and I will continue probably with this lecture to finish the chapter 3. Then only we can go to the tutorial for chapter 3. Okay, so thank you everyone. Have a good evening. Have a good